Right. Now today's class is about Newton's third law of motion. Right. So we have done the first law, second law, and today's third law. Right. With that, all the laws of Newton is over. Newton's third law of motion. Newton's third law of motion. So I think even everybody knows about it. Even those who are not familiar with physics, they are also aware of this theory, right? Uh, eh, what this theory is about. Very very good. Every reaction has a equal and opposite reaction, right? Okay. Newton's third law of motion. Yeah, every action has a equal and opposite reaction force, right? Um, so in brief, it is right. Whenever whenever two opposite bodies interact, the force they exert on each other force they exert on each other are equal in size and they act in opposite direction, right? And now of the same type, both forces are of the same type, right? There are different forces now, so uh, the reaction force is also of the same type and are of the same type, of the same type. In brief, you can tell you every action has a uh, reaction of equal size and opposing direction. Right. Now let's say you can apply the Newton's third law of motion. Uh, can you explain applying this Newton third law of motion? Uh, how a person can walk on the ground? Right? Can you apply Newton's third law of motion when a person is walking on ground? Can you apply and tell me when a person is walking on the ground? How do you apply? Person walks on the ground. Where do you apply? In which place do you apply? And how are you going to apply that? Yes. Yeah. So, for example, it is actually foot, right? Foot and the toe, actually, right? So you are walking by exerting a force on the ground from your toes, right? That is how you walk. So if this is your toe, so from your toes you are you are uh, you are actually pushing the ground against your movement. So if this is the ground, so from your toes you are exerting a force on the ground, right? And equal amount of force is there on you also. Now you be careful. Now you may feel like it is on the same place. No, now this is in red color. It is a force on the ground from the foot. Otherwise, you may feel like it is like balanced. No, if the forces are balanced, there cannot be any acceleration. No, we are talking about the reaction force is on the opposite object, right? Not on the same object, right? So therefore, the red color one is from the foot on the ground, right? Force on ground from foot, ground on ground from foot. In green color, we have force on foot from the ground. Force on foot from the ground. Okay. So these two forces, both are same in size, opposite in direction. These are vector scales, right? And the force in red color is on the ground, force on the green color is on the foot, right? So in other terms, you can tell, as per Newton's third law, the foot pushes the ground backwards and the ground pushes the foot forwards, right? Foot pushes the ground backwards and the ground pushes the foot forward. Ground pushes the foot forward, right? The foot is moving from the force that is exerted by the ground, right? Right, Now I will give a diagram as a question. There's a book on the table. This is the reaction force. So it is on a table, right? Reaction force. And here we have the weight. It is on the table. This diagram can be explained with which law of physics? Right? This diagram can explain which law of physics? Is it the first law of Newton? Is it the second law of Newton? Is it the third law of Newton? Which law can describe it? Can you tell me? Which law describes it? And you should send the answer to me. Using that law, explain it. Either could be the first law, either could be the second law, either could be the third law. Which law can be applied here? Okay. Ah, is it Newton third law? Right. Book pushes the. So in this diagram, can you can you see any force from the book on the table? Can you see it? Can you see any force from the book on the table? Wait, here. No, weight is from Earth on the book only, right? So both these forces are on the book. From the one is from Earth as gravity, other one is from the table. Both these forces are on the book itself. Newton third law is explaining when it is applied on two different objects, pair of objects, but here on the same object. Both weight and the reactant force is on the object. So what is this law in? Which law can explain this? Second law. Second law can be applied when the forces are unbalanced. Is it unbalanced? Then which is the law then? When the forces are balanced? First one, rewrite your answer. The forces are ba- balanced, right? When they are uh, when they are an unbalanced, when the forces are balanced, right, on an object. Either the object is moving at a constant velocity or the object is not moving at all. Yeah, yeah, it was like after 20 minutes something. No, no, it will be like 9:30 something. Okay. Now here you can explain this with the first law of Newton because forces are balanced on the book itself, right? Now if it is given like this, if I redraw it, this is the book. To apply third law of Newton, now this is the reactant force on the book from the table. This is the on the table. This is how the weight is acting on the table, right? You can see W, right? Or you can R on the table, R on the book. One is on the book, one is on the table. This can be now you. This is about the third law of Newton. Right. Now let us move on to another subunit, momentum. Right. Momentum. What is momentum? Now in the momentum there are two type of momentum. One is angular momentum and other one is linear momentum. Angular momentum studied in what? In A2s. Now linear momentum, here we are learning about linear motion, not about rotation, right? Linear motion we discussed on using those equations. Uh, this momentum is linear momentum is defined. Linear momentum is actually P, right? P equals M multiplied by V. M is for mass. Remember, it must be in the SI units, kilograms. V is for velocity, meters per square second. Now here also, since velocity is a vector quantity, direction and also it has a magnitude, right? So therefore, P is what? A vector quantity. Since it has both magnitude and direction is there. It has both magnitude and direction. So it means this can have both negative P and positive P. Uh, and the unit is what? Kilograms, meters per second. That is the unit. Uh, right. I will give you some questions. Q1. There's a tennis ball moving at this velocity and the mass 60 grams. Find the P. Question number 2. This is bumping on the wall and returning back. It's elastic. Elastic means it is coming back at the same velocity, right? Bouncing back on the same velocity. Find the second velocity after it is bounced back. It is bounced back at the same velocity. Find it. Now I was asking about momentum. So remember now it is a vector quantity. P equals mv. Usually from the left to right it is positive. So mass is not a vector quantity, it's just a uh, scalar quantity. So anyway, it must be in kilograms. In kilograms is 0.060 multiplied by 2. Right? So you are getting 112, right? 0.12, right? Kilograms per meter second, right? And when it is bounced back, again P equals mv. Now from right to left, it must be negative. So mass is 0.060 multiplied by negative 2. Same in size, magnitude, in direction it is opposite. 0 minus 0.12 kilograms per meter second. Is it clear? Now it is negative. No? Okay. Right. I will give another question. Uh, there are two objects. One is a tennis racket. Now, tennis racket is what? Now, from the tennis racket, it is being bounced off a tennis ball of 60 grams at a velocity of 75 meters per second. And other thing is there's a brick weighing 3 kilograms moving at 1.5 meters per second same direction. Find their momentum separate. Applying the equations. Right. So here you are getting it as both. Yeah. Even though the masses are different, since the velocities are different, the multiplication is the momentum, right? Same momentum you are getting. Sorry, this one, right? Same momentum. Even though the objects have different masses, the multiplication is what matters. So let us move on to just like the Newton's theory, there's another theory. If you can remember in the lower grades, you learned about conservation of energy, the first law of thermodynamics. Just like that, there's another law on physics, the three laws of physics, Newtonian laws, and another law, conservation of linear momentum. So one of the easiest. Conservation of linear momentum. So this tells you for an object having a momentum, right? If it hits on another object, the total momentum of the both the objects are going to be the same. Before the impact and after impact, before the collision and after the collision, the total linear momentum is going to be the same. So remember, now we are talking about a closed system. You know what a closed system is. Only energy can be exchanged between the system and the surroundings. Right? Mass cannot be exchanged. In a closed system, in a closed system, total momentum before collision. Before a collision is equal to total momentum after a collision. So with a diagram I will show you here. If there is an object with M, it is having a momentum of U, and there is another object having mass M, let's say a larger mass. It has zero velocity. It does not move. It has zero velocity, and they are colliding each other. It is on the collision path. They are colliding. After collision, this is what, moving back at a different velocity v. Here, the larger object is also obtaining a velocity while it has collided with the object having mass m, capital M mass. It has started to move forward with a velocity of v. So, similar velocities. Now I want you to plug in the values and find the formula for the velocity after collision v, right? I want you to find the formula using this information. Find the formula for v. V means velocity after collision. Both are moving at same velocities but in different directions. I want you to find a formula for velocity v using these values. Can you do it? Plug in the values and find. Initial momentum versus final momentum. It's easy, right? Before the collision, m into u. Now here the momentum is zero, no? So m into zero is zero. After collision, m multiplied by v, but it is negative v, right? Other side. Here, m into capital M now. My both terms look similar, right? Capital M into v. So you just need to make it a subject. So when you make it a subject, it becomes what? Now it is mathematics, your basic mathematics. When you make it the subject, it is what? Mu divided by m minus, simple, right? Okay. Now if they have given you some values, you can plug in the values and find it. Right? Don't memorize this formula. It depends on the question or the scenario given. Right? I just gave you a question, so they may give you a question like this, right? Before collision and after collision. Okay. Before, yeah, after. All right. Now I will give you a question. Q. Uh, there's an object on wheels moving at 3 meters per second. The mass is 1.8 kilograms. There's another object. It is not moving before collision. After collision, both are moving together. They got stuck onto each other. Right? Both these objects are having the same mass. Find the velocity after collision. Right? Use the conservation of linear momentum. Simple as that. Before collision, 3 into point 0.8. After collision, B into 1.6. So V equals 3 into point 0.8 divided by 1.6. 1.5 you got, right? Meters per second. After. Yes. Now let us see why you can apply conservation of linear momentum. Why it works like that? Why the linear momentum is always conserved? Right? What is the reason for that? Right? The reason is, so let's discuss. Let's put on the heading like conservation of linear momentum and Newton's third law. What is the connection between? Conservation of linear momentum and Newton's third law. So remember now when they're colliding onto each other. So now I'm talking about at the collision. These are the two objects on wheels. Right? So irrespective of their masses, keep that in mind. Irrespective of their masses, as per Newton third law, right? Now they have collided actually, right? They have collided. Should be at the moment of collision, right? Now at the collision, equal and opposite forces are acting against it. In red color, I am talking about on the red color trailer. In blue color, on the blue color trailer. Right? Equal and opposite forces, reactive forces. If this is A, if this is B, this is FBA, from B to A. This is from what? A to B. Force from A to B. Equal force at the collision, equal force. When they are hitting on to each other, just like when you are clapping also, right? On the two palms of your hand, equal and opposite force is acting on you, on your two palms. Same size, opposite in direction. Similar thing happens here, right? Magnitude is the same, but people different direction, right? Now what happens? Now we know this force is causing a what? Now, for example, before collision, the red color is acceleration, right? Because of this force, there is a deceleration of the object, a sudden deceleration. That deceleration is equal to what? M into A minus MA. This side. No. So I am talking about the magnitude, right? Irrespective of the mass. This is the red color. And for this object also, we can plug in the values. Because of this force, it is starting to accelerate. That is why it has the movement after collision. Let us plug in that one. I will do it red color. FBA. FBA equal to minus MA here. Right? Uh, this one you can write it with blue color. FAB is equal to again whatever the mass it has plus MA. Right? So whatever the magnitude of MA decrease from the red color trolley, whatever this value, similar amount has been increased for the other trolley. This has gained, right? The gained amount of M multiplied by A for blue color trolley is equal to the lost amount of M multiplied by A of red color trolley, right? So therefore, what happens? Equal amount, whatever decrease from red color A has been gained by the blue color trolley. So that is why before collision, whatever the momentum this had, whatever the p value it had, has been conserved after collision. Why? We are talking about a total momentum. Total momentum means the addition of the momentum of both these trolleys. So whatever the momentum initial had is still there in the whole system. We are talking about the both trolleys after collision. Why? This force has reduced the momentum a bit of red color, but when you talk about the blue color, that reduction has been added to the blue color. So whatever being reduced has been added to the blue color. So therefore, when you take the total impact is zero because of this collision. Is it understood? Whatever being lost here in P, right? In momentum, whatever the lost in momentum of red color has been gained by the blue color. So when we are taking the total, so there's no change in total value. It means initial value of before collision still is there. So that is why we can write the conservation of momentum. Why? Before momentum has been preserved. After at the collision also, whatever being reduced of red color has been gained by the blue color. Is it clear? Yes. That is why we can apply this. Right? Um I will give a question. Very interesting one, huh? Think and write. There's a person on what? Wheels, right? They have this skating wheels, right? I don't know what the specific name, right? Skating, right? Yeah. They have this. He's on skates. So now, no, we can imagine. We can tell zero friction because he's on wheels. No, assume he has a foot pole and the mass of this man is 80 kilograms. Mass of the ball is 1 kilogram. Let's say massive ball, right? He is throwing this ball forward. He is throwing this ball forward with a velocity of 40 meters per second. I don't know, hypothetically, right? The velocity of the man moving forward. Find this value. After he has thrown it backwards, actually, right? Find the u value of man. Can you do it? Apply the suitable equation with the suitable law and find. Initially, total momentum was zero because no one is moving. After that, let us make it negative here. 1 kilogram multiplied by 40. Other way around, if it is positive, u multiplied by 80. So u equals 40 divided by 80. Yeah, so therefore half meters per second, right? Yeah, half a meters per second. Very slowly is moving forward, right? So our ice skaters, they know about this because they are experiencing it. And yeah, when they do these, aerobic displays, right? Because they are actually in a near frictionless environment because they are on wheels. So they are nicely, maybe knowingly or with their experience, they are using these laws in physics because they are in an environment where frictionless environment nearly, right? So they can actually, you can do many experiments in physics when you are on wheels, right? On, like, yeah, on skates on ice you can do it, right? Because it's a very laboratory like condition, because in normal environment you have a friction, right? So yeah, so very difficult to test these experiments in real life, but on ice or on wheels, you are getting the near perfect conditions, right? So that's all for today, and we are going to sign off. Take care, bye bye. See you. And next week it is about moments, right? Moments. Good night. Take care. Bye bye. Okay.